Okay, so now that we've talked about the universal law of gravity, let's do a few examples and see how this actually works. So the first example we're going to look at is, let's say here we are, and here I am with my plumb bob. So here's my plumb bob, where I'm hanging this thing down, where the length of the string L is equal to 0.5 meters, and this has some mass M to it. Again, when I don't tell you mass, that means it's going to cancel, so don't freak out. I'm then standing some distance away from a mountain, where I'm going to approximate that mountain then as a spherical boulder, basically, whose radius is 2 kilometers and has a mass density of 2.6 times 10 to the third kilograms, where I'm standing, say, over here, a distance of 3 times the radius away from the center of this object. And what I want to know then is, so if my key should be hanging like this, but now it's feeling a force in this direction, it's going to be pulled to the side. I want to know by how much is this thing pulled to the side. So what is that amount of x? So let's draw a free body diagram. So here we're going to have what? So here's the length of my string. Here's the mass. So we know we have mg down in this direction, right? So this is feeling gravity in this direction. But there's also the gravitational attraction due to this boulder in this direction. So we're going to have f of g pulling in this direction. And we know that what? This has a length of L to it. So here is L. And this is going to not be accelerating, so this is going to be a static situation. So here we're going to set up our coordinate system. So this is going to be a y direction and say the x direction. So that this is going to be at an angle of theta. And in my string here, we have to have a tension. So let's draw a tension force. So this is my tension of T. So good. So like I said, so ultimately what we want to know then is, if I drop this guy down here, so that this is also the angle of theta, what is this displacement here? So by how much x is this guy being displaced away from the vertical? So this is what we want to know. So those two angles are, sorry, you're that angle in the wrong spot. This should be, oops, this angle, theta, good. So that those two angles are the same. Good. So again, since it's a static situation, so what we know then is that what, the sum of the forces in the two different directions must be equal to 0. So let's look at the x direction first. So we have the sum of the forces in the x direction must be 0. So here I have this portion of the tension. So that is going to be the sine portion of the tension and the gravitational force. So I get t sine of theta minus the gravitational force is equal to 0. And then the sum of the forces in the y direction also must be equal to 0. So here I have this portion of the tension, which is the cosine portion, and then the weight. So then I have t cosine of theta minus mg are all then equal to 0. So basically, combining these two things together, I can now determine what is the tangent of the angle. The way I can do that is I can use this one to then solve for the tension, and then use the tension back into here to then find the gravitational force. So let's plug that in. So from here, what I get then is that the tension is equal to the weight divided by cosine of the angle. Plug that into here, then I get the weight times sine of the angle divided by cosine of the angle, but that's simply the same thing as tangent. So this is then going to be mg times tangent of the angle is equal to the gravitational force. So let's rewrite that over here and let this guy out in its full glory. So this is going to be m times g times tangent of the angle is then equal to the gravitational force, so that's capital G, times the mass of the plumb bob, which is the same as this mass, times then the mass of the boulder, but since I didn't tell you the mass, but I told you its radius, and I also told you its mass density, then the mass then is simply going to be the mass density times the volume. So let's write that down. So this is going to be the density times the volume. I'll leave it that way for now. Divided by the distance between the two, but as we're told in the problem, distance between the two is 3 times the radius. So this is then going to be 3 times the radius quantity squared. So as promised, what happens is, since I didn't tell you the mass of the plumb bob, or the mass of my keys in this case, those are just going to cancel out, so we don't actually care. And let's solve this for the tangent of the angle. So we get tangent of the angle then is equal to, pardon me. So it's going to be g times the density times the volume divided by g times 3 times the radius squared. Now remember, volume of a sphere is equal to 4/3 times pi times the radius cubed. So when I multiply this out, this is then going to be equal to 4/3 times g times pi times rho times r cubed, all divided by g times 9 times r squared. So that's going to cancel with that. So at the end of the day, what I get is what? This 3 will cancel with that, which gives it 3. So this is going to be what? 12 times g times pi times rho times r, all divided by g. So this is now going to give me the. No, that doesn't cancel with that. I think it's multiplied with that. Sorry, so it's going to be actually 4 times 27. Sorry about that. There we go. Okay, now we're back on track. Good. So where am I? Good. So now we need to use this angle then to determine that distance. Now, so what do we know? So we know that what? Tangent of the angle is actually going to be what? The opposite side, which is x, divided by the adjacent side, which we don't know what it is. But what we do know is actually the hypotenuse. So we could say that sine of the angle is actually equal to what? X divided by the length. Now, but in this case, we have a tangent of the angle, not sine of the angle, but what type of deflection are we going to be considering here? So this has a length of L, and I have something massive over here, but we know the gravitational force is actually very small because G here is times 10 to the minus 11, which means that this thing is only going to be deflected by a little tiny bit. So if this is only deflected by a little tiny bit, what that means then is that this angle is going to be something very small. So if I'm dealing with a small angle, well, it turns out that under small angle approximations, sine of an angle is approximately the same thing as tangent of the angle, which means that we can actually use the sine here as the x over L in replace of the tangent. So the left-hand side then is going to be simply x divided by L. Good. So from here, we can solve for x, which again, x is going to be this displacement. So let's get rid of this. And multiply it simply by L. So finally we get x then is going to be equal to 4 over 27 times g times pi times rho times r, all divided by g, and now I need to multiply by L. All right, so plugging my numbers, what I get in this case then is this works out to be about 8.2 times 10 to the minus 6 meters, which is 8.2 micrometers, so micrometers. So the deflection at my keys then feel to the right, my right, your left, would then be a slight amount of about 8.2 micrometers. So with my naked eye, I could actually see that happen. It'd just be too small. But it is deflected nonetheless. Good. So now, the next example we're going to look at is what happens when we have discrete masses. So here, we're going to have then a square, where the square then has equal sides of length of 20 centimeters, and then we're going to have different masses associated here. So this is my configuration. So here I have mass 1. This is side length of, say, A. Here's mass 2. Side length of A again, because this is a square. This is then M4. Side length of A. This is then M3. And side length of A. In the center, we're going to put another mass, M5. And ultimately what we want to know is, what is the force on M5? So what's the force on him? Now, let me give you some numbers. Side length A is going to be 20 centimeters. M1 is equal to 5 grams. M2 is equal to 3 grams. M3 is equal to 1 gram. And then finally M4 is equal to 5 grams. Okay, so again, what I want to know is what is the direction of the net force onto M5? So good. So here, since I have multiple masses, each one of these guys are then, again, just point masses. What that tells me is we can use the superposition principle, which means that the net force on 5 here is simply going to be equal to the vector sum of all the different forces acting onto 5. So let's draw this. So basically I'm going to have a force in this direction on 5 by 1. So this is going to be 5, 1. Force in this direction by 2. Force in this direction by 4. And then a force in this direction by 3. Now let's look at the masses real quick. So first thing we can see then is that what? M1 and M4, which is this mass and this mass, actually have identical amount of mass to it. And this one has, obviously, the same mass as itself, which basically means that this distance here is exactly the same as this distance here, because this distance is the same everywhere. Which means since this distance is the same as this mass is the same as this mass, that means that this force here and this force here are actually equal and opposite to each other. So M1 is pulling M5 towards itself as much as M4 is pulling M5 towards itself, which means that the vector sum between these two forces cancel. So here, the only force that's going to be on this object is then going to be the force in this direction. So from M2 and M3. Now the other thing we can see is since M2 is bigger than M3, that means the force from 2 is going to be bigger from the force from 3, which means ultimately it's going to be pulled in the direction of 2. So this is what we call using symmetry. So basically what we're doing is we're simply looking at how these forces are related to each other and see if there's any symmetries here where, again, this one and this one have symmetry. So in this case, they're going to cancel with each other and everything's along this line. But again, the size of this force should be bigger than the size of this force, which means ultimately this thing has to be pulled at a 45-degree angle. Now, if I put in a coordinate system here, so if I call this my y direction and I call this my x direction, then we know the direction of the net force is going to be here. So this is going to be F5, which ultimately is going to point out a 45-degree line. But the 45-degree line is the I direction plus the j direction, because that's a 45-degree angle. So, good. So ultimately what I know then is what? That this is going to be equal to then the difference then between the 5 and the 3 forces. And this is only going to point along the 45-degree line. Now, but the other part is, it's the difference between the 5 and the 3, but not in the x direction, but only in the y direction. So in this case, I'm only considering this particular direction. Coordinate those angles, and again, this is going to point in the I hat plus j hat directions. So good. So let's put in numbers. So use gravitational force. So it's going to be g times m5 divided by the distance, right? Because this distance here is the same as this distance, so we just call that distance squared. Times then m2 in this case minus m3, all in the I plus j direction. So that's the direction at which it's going to point. Now let's determine what d is. So if I look at here, so this side is A, this side is A. This from here to here then is equal to D, which is the same as this distance, which is equal to D. Good. Now what I know is by Pythagorean's theorem, this is side A, this is side A. So here I have this distance here, which is what? 2 times D quantities squared is then equal to A squared plus A squared, which is the same thing as 2A squared, which means that what? 2 times D is then equal to the square root of 2 times A, which means D then is equal to what, the square root of 2 over 2 times A. So let's plug that in. So it's going to be the same thing then as g times m5 divided by, that's going to become 2 over 4, which is 1/2. So the 2 is going to move to the top. A squared all times m2 minus m3, and the I hat plus j hat direction. Good. Plug in my numbers. What I get in this case then is this works out to be about 1.179 times 10 to the minus 14th newtons in the I hat plus j hat direction. So this is the net force on mass 5. So again, anytime we're presented with problems like this, the first thing we always want to look for is this idea of symmetry. Are there any forces that are the same? Is there anything that automatically going to cancel from each other? Because if that's the case, then we don't have to worry about writing out all these particular forces, because all we're going to do is multiply things and subtract things that are all the same, and it's just going to be a whole bunch of waste of time. So there's no point doing that. So the best thing to always do is always to look for this symmetry. So is there anything that's actually going to cancel, and how do they cancel? And let's get rid of them. So let's do another example. So the next one is, let's look at one with a continuous mass distribution. So let's say that we have a mass m here, and then some distance over here we're going to put a rod. So let's say this is a thin rod, where this thin rod has a length of L to it. So this thing has a length of L, and these two are separated from a center-to-center distance of d. And what I want to know then is, what is the magnitude and direction of the force on this mass here? This is what we want to know. Now let's put in some numbers just for fun. So we have d that is equal to 23 centimeters. So the distance between the center of his and the end of the rod is 23 centimeters. The length of the rod is equal to 3 meters, and this rod has a mass where that mass is equal to 5 kilograms, and this mass here has a much smaller mass, which is 0.67 kilograms. So good. So okay. Now, since this is a rod, this is a continuous mass distribution, so I have something like this, and as we talked about when we did moments of inertia, this thing has a line symmetry to it. So basically, we're assuming that this thing is more like this, where it's much thinner. So in this case, all of the matter is confined across the line, which means that we're simply going to cut this thing up into small dm's. So this is going to be my dm. And in this case, we're going to rewrite dm as then the linear mass density times dl. And now let's put this in the coordinate system. So let's say that here is the center of my coordinate system. So this is my origin. So I'm going to call that the y direction. And let's call this the x direction. So in this case, dl, which is the width of this section, is the same thing as simply dx. So automatically I can say my dm then is going to be lambda times dx. Good. Now what? So what's r? So r, again, is the distance from here to the location of the mass, or my differential mass in this case, so this is my r. Now again, since this is all completely across the x-axis, r in this case is simply equal to x. So we can then say that the force on m, magnitude-wise, is then equal to g times m times the integral of dm divided by x squared, where again, dm is the same thing as lambda dx, so it's going to be the same thing then as what? G times m times lambda times the integral of dx divided by x squared. Now, when I do things like this, I have to integrate over where the mass actually exists. Now, in this case, the mass only exists within the rod, i.e. within this rod, which means even though my coordinate system starts here at this mass, I'm not going to integrate from here to here because there is no mass in that stage. So I'm going to start my integration where the mass actually starts, which is at D, and then integrate along the entire length of this to the end of it, and then nothing after that because, again, there is no mass contained after that. So this thing is starting at D, this thing has a length of L, then I'm going to integrate from D out to the length of this, which is going to be at D plus L. So here, our bounds of integration then are going to be from D to d plus L. So good. So from here, you can then say that's what? Integral of 1 over x then is, or 1 over x squared is a negative 1 over x. So I get a negative gm lambda divided by x evaluated from d to d plus L. Good. So I plug this in, so then in this case I'm going to get a g times m times lambda times, so I get a 1 over d minus 1 over d plus L. And again, here I'm switching the order because I'm bringing in that negative sign, which then switches the order of those two. Now here the common denominator is d times d plus L, so here I get my force on m is then equal to g times m times lambda times, so I get a d plus L minus d, all divided by d times d plus L. Yeah, so here I'm multiplying this, multiplying that one by d, so my d's are going to cancel out. So at the end of the day, I get a g times m times lambda, all times L divided by d times d plus L. Now remember, lambda is the mass per unit length, so in this case, lambda is equal to the total mass of the rod divided by the length of the rod. So substituting in here, that length's going to kill off this length, so finally I get g times capital M times little m, all divided by d times d plus L. And if I wrote this as a vector, we know in this case then is since gravity is an attractive force, this guy's going to feel a force in this direction, which would be in the positive x direction or in the I hat direction. Now, substituting my numbers, what I get in this case then is that the force magnitude that this thing feels is then equal to 3 times 10 to the 10th newtons in the I hat direction. So a nice continuous mass distribution. So let's do one more. Let's do one more with an object which is rotating. So now that we have both the gravitational acceleration and that centripetal acceleration. Try to get rid of all this chalk dust. Apparently they didn't clean the rooms, but that's fine. That's fine. Okay, so in this one, what we're going to have is a pulsar. So a pulsar is actually a neutron star whose magnetic fields are so large that it's actually creating radiation. That radiation is being blown away from the poles, and then that is giving us light. So here's my pulsar. This thing is rotating about its axis with an angular frequency or angular velocity of omega. And this thing has a mass which is equal to the mass of the sun. So the mass of this is equal to 1 solar mass, where 1 solar mass is equal to 1.98 times 10 to the 30th kilograms. And this thing has a radius r, where that radius is about the same size as something smaller, so 12 kilometers. Now, we're not told the angular velocity, but we are told the period. What we said is that this thing makes 1 complete revolution in 0.041 seconds. So, we then want to know, in this case, if I'm on the equator, so say this is a point on the equator, we want to know what is the difference between the local acceleration, g, and the acceleration due to gravity, ag. So what is the percent difference at this point? So we want to know what is the percent difference at a point along the equator, which is going to be the difference between the local gravity, which again, the local gravity is going to include both the acceleration due to gravity and that centripetal acceleration, and just the acceleration due to gravity. So So let's look at a closer shot. So let's say I was standing here. So this is me standing here. And we know is that I'm moving in a circle, so I have a tangential velocity at this point. It's into the board. which means I have a centripetal acceleration towards the center. I have this AR towards the center. And what else? So we also know that I'm going to feel a weight. So I have a weight down in this direction. So let's call that MAG, where this is the mass times the acceleration due to gravity. But I also have a normal force, so let's assume I'm kind of like standing on a scale. So in this case, I have a normal force pointing in this direction. So this is my normal force. Okay. So basically, if I was standing on a scale, what the scale would tell me would be my mass times my local acceleration. Right? So if I was standing here on a scale and I look down, what I see is that I weigh a certain amount. That certain amount is going to be my mass times my local acceleration, which basically means that this is going to be the same thing as m times g, which is the net acceleration at which I feel. Now, since my acceleration is towards the center, let's take this as my positive y direction. So here I can say, well, the sum of the forces in the y direction then are equal to my centripetal acceleration. So this is now going to be my m times ar. And then that's equal to my MAG, which is my weight due to the fact that I have a gravitational attraction, minus then my normal force is then all equal to MAR. But again, this is going to be M times AG minus MG is all equal to MAR. Now, since all those masses are the same, so you can cancel out those masses, so this says then that the difference between the local acceleration and that of the acceleration due to gravity is simply equal to that radial acceleration. Now, what I want to know is the percent difference. So the percent difference then would be simply to take and divide both sides by AG, and then multiply by 100 to get that net percent difference. So this says then that the difference between the local, or the acceleration minus the local acceleration, is simply equal to that of the centripetal acceleration divided by the net AG. Now remember that this guy is the same thing as r times omega squared divided by AG. And then what I want to do is turn omega into the period, right? Because we're given the period, we're not given that angular velocity. So to do that, remember that period is the same thing as 1 over the frequency, but we also know that 2 pi times the frequency is equal to the angular velocity, which means that the frequency is the same thing as the angular velocity divided by 2 pi, so this is going to be the same thing then as 2 pi divided by the frequency, or sorry, the angular velocity, there we go, which means that the angular velocity then is 2 pi divided by the period. So if I put that in here, then I get AG minus G divided by AG, that is equal to R, which is the radius, times then 4 times pi squared, all divided by AG, times then the period squared. Now AG is the acceleration due to the fact that I'm on the surface, so it means that I have m times AG is equal to the gravitational force, which means m times AG then is equal to g times the mass, in this case the solar mass, times the mass of me divided by the radius squared. So this mass is going to cancel this mass, which means AG is given this way. So let's put that in here. So finally this is going to become what? 4 times pi squared times r squared divided by g times the solar mass times the period squared. Or finally, I get 4 pi squared r cubed divided by g times the solar mass times the period squared. Plug in my numbers. What I get in this case then is this works out to be about 3.06 times 10 to the minus 4. Or, since I want the percent, all I have to do is multiply this by 100, which means my percent difference is equal to 3.06 times 10 to the minus 2, which means that we're at about 0.0306% difference between the acceleration due to gravity and that of the local acceleration due to the fact that there is this centripetal acceleration as well. So again, typically this is going to be some sort of small effect. right? This thing has a ridiculously high velocity since its period is very small. Unlike, say, on the surface of the Earth, where on the surface of the Earth we have a very small angular velocity, so that's going to give us a very small contribution. But again, that contribution is enough to basically cause our Earth over time to have deformed and changed shape.